Now we get to talk financial math. This is the fun stuff. Like, how do you make a bunch of money? So I'm going to bring up just a couple things to remind you. These are quick and easy. Grab a calculator. Let me show you how to set these up. Now, you get to write it on there. Let's talk about how much money you can make over a period of time. We've dealt with these two formulas. Now, the only thing that we haven't talked about is your textbook and other textbooks, they vary on what they call these different units. This is an annual model. If we do annual growth for a particular percentage rate, that's an annual model. Down here, that K, remember I used N the other day instead of K, and that just depends on what textbook you're using. K stands for, if you look inside here, it's the number of compoundings in a particular period of time. So let me just label what K is. So we talked about infinite compoundings and how much it was if I compounded it every day, every hour, every minute, 525,600 minutes. We found out that this lovely little piece right here, if you make K infinite, the limit as 1 plus R, if I do it every single moment of every single day, I showed you guys a little graph, this made E. And if you want to see that again, I'll show you where it came. Where are you, little graph? There it is. This graph is right here. Come on, big screen. That 1 over 1 plus, as we compounded forevermore, if I can get my graph to work. No, right there. And it's 1 plus 1 over x to the x. As x goes to infinity, this graph doesn't get bigger and bigger and bigger. It heads toward a plateau, an asymptote. And that asymptote, you can kind of see here, is 2.71. Over here is a table on the right of values as x gets bigger and bigger. Those numbers on the left are x's. But you don't get any bigger, you just get more and more decimals. 2.71 something, 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 3, 2.713. That's E. It's a magical number. Okay? So, back to this, that limit as that K got bigger and bigger, that graph that we saw, ended up being E, that 2.71 number that Rachel loves so much. So, if I use these two formulas, they're just for different situations. So I'll help you set up these. Like suppose Quan Lee wants to invest 500 at 7% interest compounded annually. The model above, if I apply it appropriately, would just look like this. And she says, I want to invest for 10 years. The exponent is your years. So in this model, your exponent years happens to be an N. It's just a different textbook take. R is the percentage rate as a decimal. You always use a decimal. So that's it. That's the setup. You put it in your calculator. It's a super quick calculation, 500. In parentheses, 1.07 to the 10th. You get 983.58. And you round to the nearest cent, obviously, if you're dealing with money. Done. So it's a quick model, quick entry. Down below, it's compounded multiple times, K times per year. I used N the last time, so K is the multiple times we invest it. The setup for this one, 500 for Roberto. He puts 500 in there, and it's not 9%. It's, remember, 9% busted up into K parts, and K in this case is monthly, which is 12 times a year. Monthly means 12 times a year. K equals 12 when it's monthly. So 12 to the 12. And this also, the value of the investment after 5 years, that means you're going to put years in as 5 down at the bottom. So just busts up that 9% into 12 equal installments instead of just doing it all at once. And it does make a difference. You guys know that compounding more and more often doesn't make a difference after a while, but it can make a difference if the difference between doing it every year and doing it every 12 months or monthly over a period of a year, that does make a difference in the outcome. You do get a different result. So let's do this. I'm raising it up to the 12 times 5, which is 60. I think I get 782.84. Okay, so you get a certain amount of money. And I know you can enter that in the calculator. No big deal. The interesting part is when we get to comparing these and saying which one's better and what that means if it's better. So on the top here, your sheet on the next page is I'm annual interest rates. How long will her investment grow till 3,000? Now there's some solving stuff. So this is like where we were before. If you use an annual interest rate of 9% and you compound annually, as this question calls for, it says compounded, actually this one's compounded monthly, so it's underline everything. How long will it take for investment to reach 3,000? We're getting to 3,000 bucks starting with 500. It's just like the last problem, it's compounded monthly. But the part that's left open that I don't know, and I'm going to use t because t just makes way more sense for time for me. I know I'm going to get to 3,000 eventually. I just don't know how long, how many years it's going to take. The 12 isn't the number of years. 12 is the monthly compounding piece. It's breaking up the 9% into 12 chunks, 12 equal chunks. That part of solving is what we just got done with. You guys are experts at this. Dividing by 500 on both sides, dividing by 500 on both sides, and getting 6, and then you solve from there. 6 equals, and I have some numbers for these that we'll just use and go from there. Okay. Solve a 6 equals that dude. And then you take the log of both sides. To get the whole purpose of log of both sides, like we were talking about before, is I need to get to a variable in the exponent. That's when a log occurs. If you have an exponential function, something raised to a power, a variable power, this is when you take the log of both sides. So thanks, Nick. That was the kind of thing we wanted to point out because we've got to be extra careful. If I got a variable in the exponent, this is when I introduce the log of both sides. That's the time for it. And then you can roll out from there. So this allows us to rewrite this as 12t ln 1 plus 0.09 over 12, like that. The rest is some nice algebra. I want to get t by itself. I got to divide away the rest of that stuff. So I'm going to do it in one fell swoop. I get t equals log of 6 divided by all that other stuff, divided by 12 and the log of 1 plus 0.099 over 12. When you want to divide away stuff, if I'm going to divide away 12 and I'm going to divide away this log number, you can do them at the same time. So that's what I've done over here. End result, there's a total of, t is about 19.98, roughly. So it's about 20 years, which is kind of a cool take at it. I mean, if I put in 500 bucks at 9% interest, when will it be $3,000 with no contribution whatsoever on my part? It takes 20 years. That's a long time. It's not so fun to let money just sit there, especially a small amount. We want to know how to make big bucks, and that's what's coming next. So Stephen, thank you for volunteering for this problem. I want to know if I compound quarterly, how much, I want to basically double my money. How long will it take to double? If you start with 500, that means you're going to end with 1,000. So it's the same as the last problem. It's compounded quarterly, so watch the setup, and it's a different interest rate. Quarterly doubles his money, and the interest rate on this one is, oh, that's what I want to find. That's crazy. Quarterly means 4 times a year. And it says it takes 10 years to double, so actually I know the years. This is a little different scenario. What I don't know is the number of years. I know it will double after 10 years. I'm sorry, I don't know the rate. I know it'll double after 10 years, compounded quarterly, but I just don't know what the rate was. So this is another type of solving. But you notice, this is the big key. I do not have a variable in the exponent. The variable is somewhere else. So this is not a situation where I have to do logs. It's not an exponential scenario. But I do get to solve. So you divide both sides by 500, which you know so well. But I do need to know, how do you get rid of this 4 times this 40? You know, a quick way. You can do the log of both sides, but that'd be troublesome. What gets rid of a 40 power? How do you get rid of something that's squared? Square root sounds right. If this were the second power, yeah. That's the right idea. You got it. That's exactly right. And we do it with fractional exponents. So good. And that'll take care of both sides. So if I do the 1/40th root on both sides, that takes care of any of that. So bam, bam, 1/40th on this side, gone. So 2 to the 1/40th gives me that 1 plus r over 4. Now we're home free. I got to subtract 1. So 2 to the 1/40th minus 1 equals r over 4. Multiply both sides by 4. You can get our rate. And I'll tell you, calculator will spit out 0.0699. So about 7% interest is what will allow it to double in 10 years. So about 7%. Okay, not so much. The last part, compounding continuously. So these have been quarterly and monthly, and we could do it by the minute, but to do it continuously is that magical e business that we found that if you do it all the time, it just ends up being e to the r. This is compounding it every second of every hour of every day, and it sets up really nicely. The amount of your annuity is, you start with 100, e to the rate 0.08, and then you just have to substitute whatever time you want to put in there. That's the model for this one. It says at the end of each of years 1, 2, and 7. So if I put in 1 year, if I put in 2 years, if I put in 7 years, I'll do one of them at least. So 100, and then you do e on your calculator to the 0.08 times 1, 108.38 or 33. Big bucks. If I do it for 2 years, 117.35. If I do it for 7 years, 175.07. Not a lot of money going on. We need more. We need something better. So tomorrow we'll play with the idea of which one's better, and that's this. Annual percentage yield allows you to compare annual percentage yield is a way of comparing the rate or compounding scenarios that we know, and that we'll look at mañana, because I want to give you guys time to work, but I do want to get to making the big bucks, these last two. It's called future value and loans, mortgages, present value. This is the part the other day where if you make a contribution of some kind, it really makes a difference. So let me show you my spreadsheet, and then I'll show you the same thing happens in this formula. So the fun part is you have a little money. So we got to find how much money you have. So we need to get one of you to tell us how much you currently have saved. So if I just randomly, I need your saving, like a reasonable amount you have saved right now. I don't care what it is. Oh, he's gone. Great. Gee, you are dressed like G today, which is even better. How much money do you have that if somebody says throw this money in savings, what could you contribute today to savings? If you're not willing to share, just make something up. No, your money, not your mom's money. Well, that'd be fun if we could talk about parents' money. But no, we want your money. I don't want you to make an uncomfortable statement, so you can make something up. I'm totally okay with it. Yeah, what do you have in savings right now? And if you don't want to share, you don't have to. But make something up. Okay, that's very reasonable for some. Are you employed by any chance? Ooh, this is going to be even better. You are going to be the right person for this job. Okay, $1,000. Check this out. In your bank, do you see that right there? $1,000. Let's play the game of, now you could decide that you want to open up some type of